Alright, time for the very last lecture of quantitative reasoning. Hard to believe we're already at the conclusion of the course. So the last topic we're going to discuss is exponential modeling. So we already did linear modeling. Linear modeling will be useful whenever you have a fixed rate of change. Exponential modeling is going to occur when you either have doubling, halving, or a fixed percent change. So let's go ahead and suppose you got a salary of $40,000 and you get a 3% raise each year. So year 0, starting off, salary's at $40,000. Now year 1, your salary, which is at $40,000, is going to get increased by 3% of current salary. So if you remember, we were doing stuff like this in test 2. So if we compute that, at the end of your first year, your salary is going to get bumped to $41,200. And then by the end of year 2, you get another 3% raise. So if we compute that, we get $42,436. Now I want you to pay very close attention here. This is not a constant rate of increase. Going from year 0 to year 1, you got a $1,200 raise. But if we look at going from year 1 to year 2, we got a $1,236 raise. It's a bigger raise because 3% of $41,200 is going to be more than 3% of $40,000. So whenever you have exponential growth, it's constantly accelerating, little bit by little bit. We beat this topic to death when we were discussing finance. This is very, very important when discussing compounding and finance. So let's just do one more year here. 2. And we get, by year 3, salary would be at $43,709.08. You get the idea, and we'll continue on in this fashion. Now this is quite tedious, which begs the question, is there an easier way for us to play with an exponential modeling besides having to do it 1 year at a time? Well, anytime you have a percent increase or decrease, that's a dead giveaway you got an exponential model. Also, if you ever have doubling or half-life, that's also an exponential model. So if you see a percent increase or a percent decrease, that's a dead giveaway that you're going to be using this exponential model. So let's go ahead and look at this formula. The formula states Q equals Q naught times the quantity 1 plus or minus R raised to the T power. This is where Q stands for quantity. Q sub 0 stands for initial quantity. R is the growth or decay rate, so we can use this equation for growth, and we can also use it for exponential decay. T is, of course, time, and we use addition when it's growing, subtraction when it's decaying. And quick warning here, R and T must be based on the same unit of time for this model to work. Just like in the finance unit back towards the beginning of the class. So let's go ahead and revisit that example. So suppose $40,000 salary, 3% raise each year. Write an equation. Well, the quantity of pay you're getting is going to equal the initial quantity. So here the model starting at $40,000 times 1. And then you got to ask yourself, is it going up or going down? It's going up, so we use addition by 3%. So that's 0.03. Raise the T, and let's go ahead and simplify that. And 1 plus 0.03 is 1.03. Oh, and that's as simplified as we can get it. So now we don't have to go year by year. We can plug in the year we want. So it's more of an explicit equation instead of a recursive equation. So if we want to know what your salary is going to be after 10 years, all we got to do is punch in 10 for time. And easy peasy lemon squeezy, we don't have to go year by year anymore. Just raise that to the 10th power, and we can see that salary is At the 10-year mark, going to be 53,756.66. And again, verify that on your own calculator. So how long will it take for your salary to hit $50,000? Well, we know it's going to take less than 10 years, because at 10 years, you're well above it. But this time, if we look at our equation, let's go ahead and rewrite it. This time we're not inputting a value for time, we're inputting a quantity value. So we're going to set Q to equal 50,000. And we're going to go ahead and solve this equation. So let's go ahead and divide both sides by 40,000. So that's going to get us, let's see here, 1.25 equals 1.03 raised to the t. Now, in case you need a little bit of a refresher from your high school algebra class, to solve an exponential equation, you're going to go ahead and log both sides. So the logarithm is the inverse of the exponential, so we're going to go ahead and log both sides. I'm going to go ahead and use the natural logarithm. So that's ln. What you do to one side, you do to the other. And a very useful property of logarithms is that you can pull a power out front. So that lets us pull the t out front. Very useful property. So power goes down. And then the last step is just to divide both sides by natural log of 1.03. And there we have it. So t equals natural log of 1.25 divided by natural log of 1.03. And take a moment, look at your calculator, and find the natural log button. You'll see the ln button on your calculator. Go ahead and look for it. You're going to use that to type in these values. So it's natural log of 1.25 divided by natural log of 1.03 using your calculator. You get approximately 7.55. And that's about what we were expecting. We knew it was going to be less than 10 years. So we can see by the time you hit year 8, or by the time you hit year 8, your salary will be above $50,000. So a quick little recap on logarithms in case it's been a little while since your algebra class. So you can see I've summarized solving an exponential model for time. You're going to divide both sides by the initial quantity, logarithm both sides, pull the power out, and divide. And it's always going to be the same process. Now, let's look at an example where we don't know the rate. So suppose we got a particular radioactive isotope. It's got a half-life. So anything with a half-life is going to be exponential decay. Got a half-life of 7 days. Suppose you have a 20 milligram sample. So if we go to write our equation, we know the initial quantity. We know it's subtraction because it's decaying. Problem is, we don't know the decay rate. So that's a problem. We don't know what the decay rate is. So what we're going to have to do is input known values. So we know it has a half-life of 7 days. So if I set the time value to 7, then I know the quantity is going to be half. Now we have a 20 milligram sample. Half of that is 10. So what we just did here is you got to plug in a known value. If it has a half-life of 7 days, we know that when time equals 7, quantity equals 10, and then we can go ahead and solve this. So we'll divide both sides by 20. So that's 0.5 equals 1 minus r raised to the 7. Now here we do not use logarithms. Right, we're not trying to solve for the power, we're trying to solve for the base. That's very, very different. When trying to solve for an exponent, you use logarithms. When trying to solve for the base, you use the reciprocal power. So the reciprocal of 7 is 1/7. Basically using a 7th root here. That's because inverses cancel, so those cancel. And we can type that into our calculator, so that's 0.5 raised to the 1/7. We're going to round that to 4 decimal places. That's 0.9057 equals 1 minus r. So 0.9057. And again, if you need to pause the pen cast, make sure you know how to type that into your calculator so you get 0.9057. And we're going to finish solving for r. So if we subtract 1 from both sides, we get negative 0.0943 equals negative r. Therefore, r is approximately 0.0943. So we know that this radioactive isotope has a decay rate of 9.43%. So, in conclusion, when solving for a growth or decay rate, you're going to use reciprocal power. So, quick warning. We use logarithm to solve for time. And we use reciprocal exponents to solve for that growth or decay rate. So you need to know when to use what operation. This just goes back to your standard high school algebra class. And I highly recommend right before this lecture, I recommended some reading from the book. I believe it was 9 pages, not a whole lot of reading. Highly recommend you read it. I posted it for a reason. We'll go ahead and do one last example. So here on the very last example, we got radioactive iodine-131. So radioactive isotopes are used frequently in the medical field. This particular radioactive isotope is frequently used in treating thyroid cancer. It has a half-life of 8.04 days. Suppose we got a sample of 25 milligrams. Compute the decay rate. So if we go to write the equation, so quantity equals 25 times 1, we use minus because it's decaying, RT. Now first things first, we don't know the decay rate, so we're going to punch in a known value. So every 8.04 days, write that down, we're going to have half, and half of 25 is 12.5. So then we go ahead and divide accordingly. So we divide both sides by 25. You get 0.5 equals 1 minus r raised to the 8.04. Go ahead and use that reciprocal power. What you do to one side, you must do to the other side. So type that into your calculator. So that's 0.5 raised to the 1 over 8.04. You get approximately 0.9174, rounding it to 4 decimal places. And therefore, when you're done solving for r, subtract 1, you're going to get r is approximately 0.0826. Alright, so now we're ready to write the equation. So remember, Q and T are your variables. Everything else is a constant. So 1 minus, we know the rate's 0.0826 raised to the T. Please make a note. If you need to write a note here, we're writing Q and T as letters because they are variables. And when we simplify this, this will simplify. We can do the 1 minus 0.0826. And we get 0.9174. So there's the simplified equation raised to the t. So please make sure to simplify when possible. So there's our equation. We're going to go ahead and use it now. How much of the sample will be remaining after 12 days? So all we got to do is input 12 and we are done. So this is a quickie. It's just using your equation from part C. Input 12. We'll go ahead and type that into the calculator. And we get approximately 8.88 milligrams. So 12 days later, our 25 milligram sample will have decayed down to 8.88 milligrams. And then the question is, when will the sample reach 5 milligrams? Well, we know it's going to be more than 12 days. Because 12 days we're down to 8.88. We want to know when it gets down to 5. So we're going to go ahead and plug 5 into quantity, and here we're going to have to solve for time. So I'm just using our equation that we derived in part B. Here we don't know the t value, so when we divide both sides by 25, let's go ahead and do that. That's 0.2. Here's where we're going to need logarithms. So it's when we're solving for time that we need to use logarithms on both sides. And I tend to use the natural logarithm. So just natural log both sides. That lets you pull the power out front. So natural log of 0.2 equals t times natural log of 0.9174. So therefore, t equals natural log of 0.2 divided by natural log of 0.9174. We type that into the calculator, and we get 18.67. So it would take about 18.67 days to decay down to 5 milligrams. And ladies and gentlemen, pat yourselves on the back and have a cookie and celebrate with a victory beverage of your choice. We are done with quantitative reasoning. We have covered all the course materials. So if you haven't already, go ahead and start on that test review. All we got left from this point forward is just testing and review. So keep up the hard work and let me know if you have any questions.